Okay, so hello class. So today we are going to be talking about the linear momentum homework assignment. So let's go through the problems. Okay, so problem one hazard of space travel is debris left by previous missions. There are several thousand objects orbiting Earth that are large enough to be detected by radar, but there are far greater numbers of small objects like flakes of paint. We have to calculate the magnitude of force in newtons exerted by a 0.0 or some mass of paint chip that strikes and sticks to a spacecraft window with a speed, so we'll say v, speed of paint chip, we'll see pc, and uh, and then the collision lasts some period of time of collision. Okay, so we know that J is equal to the change in momentum, and we are saying that since it's relative speed, it's basically just saying that compared to its original speed, its next speed is going to be 0. So then the momentum of the paint chip is going to be 0 at the end, and so then we have to say J is equal to mvi. Then J is equal to F delta T, and so then you solve for the force like this. So there we have it. We have F as a function of these three. Problem 2. A baseball of mass is dropped from a certain height. It bounces from the concrete below and returns to a final height. And we are neglecting air resistance here. Okay, so we have height 1, height 2, and it is dropped, so it's not thrown. So VI, when it's first dropped, is going to be equal to 0. And the baseball has some mass m. So we are finding an expression for the impulse that the baseball experiences when it bounces off the ground. And so first thing that you're going to want to do is you're going to have the two energies here. So you're going to have mgh1 and mgh2. So we can see that there's a certain amount of energy that's taken away when it collides with the ground here. And so since it doesn't return to its full height like it did before. So that's just one indication of what we can use to solve this problem. And then we know that J is equal to delta P, and this is equal to the change in momentum. So we have mv2 minus mv1, and we can just factor out an m here because we are assuming that the baseball doesn't lose anything when it bounces off the ground. So one thing that we have to know before this this ball hits the ground, we have to know what the velocities are. So one thing we can do is, so when this ball hits the ground, it's going to have all of its energy is going to be kinetic instead of potential. And so then we know that 1/2 mv1 squared is going to equal mgh1, and then we can solve for v1, and v1 is just going to be the square root of 2gh1. And we can do the same thing for v2. So then V2 is going to be equal to the square root of 2GH2 via the same process. So we're doing the same exact thing here. So then we can start to plug in these values here for V into our equation that we have for impulse, and then that will give us M, and then we have to be careful about our signs here. So this is what ends up happening is that since we have a minus here, this velocity is going to be pointed downwards since it's about to collide with the floor and it's getting closer to the ground. So then this is going to be 2GH2 minus, so this is going to be a plus 2GH1. H1. And then from here, we have the heights. We know what G is, and 2 is just a coefficient, and we have the mass of the ball. So this will give you your impulse. So now we have to find the, now it gives us a time that the baseball is in contact with the concrete. And so all we have to do is divide both sides of this equation by t to get F over here, and then we have M over delta t, M over delta t times square root of 2g, because we can factor that out, square root of h2 plus square root of h1. And there you have it. And that's how you solve for the force there. We're just basically decompressing the J from the examples that we did in class the other day. So next up we have a ball with initial velocity and a certain mass. Basically, we're just applying the concept that we learned in class. So we have a wall here, and we have a parallel and a ball that ends up striking. So this is going to be theta. This is also going to be theta. So a ball with initial velocity v and mass m strikes at a certain angle above the horizontal. The ball hits the vertical wall and bounces off so that it is again moving at 55 degrees above the horizontal with the same speed. So this is our figure here to denote that. Okay, so we have to say what is the magnitude of the impulse delivered by the wall. And so we just start with our J formula, equals delta P equals mv2 minus mv1. And so mv2 is pointed in this direction here. And what we can do is we can define this as the positive x direction instead of the negative one. And so then we can say that this is mvx plus mvx, because the v1 here, this is v1, this is v2, even though they're the same in magnitude but different in direction, we can say that these are both mvx like this, and then we can combine them into 2 mvx. And then all we have to do is use our trigonomic functions. This is going to be our opposite adjacent, so we use cosine theta. So cosine is equal to Vx over V. So then Vx is equal to V cosine theta. So now this is a function of mv and theta, and we now have what our impulse is, and then we'll just plug in our numbers from there. Okay, so a student of mass m runs at a velocity vi before jumping on a skateboard. So after jumping on the skateboard, the student has a velocity of vf. And so we have to write an expression for the weight of the skateboard. Okay, so we have to use conservation of momentum here. So before they stick together, the skateboard is at rest. So the skateboard has a mass m and a velocity of 0. I guess it doesn't. No, it doesn't have a velocity of 0, but we have our student here from skateboarding to class. And so this is before. This guy has mv student and vb. And so then after the collision, or after he gets on the skateboard, we have our skateboard and our little guy here, our student getting to class. And they have a total mass of m, this is m board, m student, of m board plus m student, and one velocity, m sb. Okay. Yeah, no, I think that the board is stationary. So VB is equal to 0. So we have to say MS VS plus MB VB, this term goes to 0, is equal to MB plus MS VSB. So now we have our statement for conservation of mass here. Okay, so we're finding a expression for the weight of the skateboard. So we're first going to find the mass of the board, and then from there we'll go ahead and find the weight, because then we just have to multiply by g, or multiply our expression by g. So first let's find the mass. Next step is going to be easier. So first thing that we have to do is divide both sides by the final velocity. So then we have ms vs over vsb is equal to mb plus ms, and then we solve for the mass of the board, and so then that's going to give us ms vs over vsb minus ms. And then so W board is then going to be equal to MSG VS over VSB minus MSG. Next is just plugging in numbers. So then part C says the student soon loses his balance and falls backwards off the board at a velocity of 1 meters per second. Assuming momentum is conserved in this process, what is the skateboard's new velocity in meters per second? Note this may not be a very good assumption, but as there is significant friction in the ball bearings and the skateboard. So we're not taking into account friction between the ball bearings and the skateboard. So we already solved for the momentum of the two here, and so now the student falls off the skateboard and sends the skateboard flying in the opposite direction, right? So we have VSF over here, and then VBF over here. Okay, so then we can say that this part is now going to be equal to them separated again. MS VSF plus MB VBF. And so we know what our mass of our board is. We have that here. And we know what VSF is, because that's what's given in our problem. And so we know that this quantity here, VSF, is going to be negative. So when we multiply it to the other side, it's going to be, or when we subtract it to the other side, the two negatives will make a positive. So we'll be adding it to this side here. And so then we'll have to divide by the mass of the board, and then that will yield us our answer. Okay. I'm going to get rid of this stuff here. Probably shouldn't have. But you can insert the expression for the mass of the board afterwards. So then we're going to get that the mass of the board times the velocity of the board final is going to be equal to mb plus ms vsb, parentheses, parentheses, plus ms vsf. And I'm going to put the magnitude sign around here so that we know that it's positive. And then we just have to solve for VBF. And so then there is the velocity of our board. And then the next part is just plugging in numbers. Okay, so next up, a young hockey goalie who weighs 31 kilograms. So he's originally at rest. He's a goalie. He catches a puck of a certain mass slapped at him at a certain speed. In this problem, take the original direction of the puck as positive. Suppose the goalie and the puck have an elastic collision, and the puck is reflected back in the direction from which it came. What would be the final velocity of the puck in meters per second in this case? So since we have to write our conservation of momentum problem, because the puck hits the goalie and then bounces back. So these two do not stick together, and so therefore we cannot put the masses together on the right side of our equation. Okay, so we have mass puck, V puck, and this is going to be our initial, and then we have that this is going to be equal to mass puck, V puck final, plus mass goalie, V goalie final. And so we can solve for the velocity in this case. Oh, we're gonna be solving for a couple different expressions. So first off, we want to get these two guys together here, and from there we're gonna write some expressions, and we'll do conservation of energy as well, because we're going to need both of them for this problem. Okay, so we can solve for this, and we can say that mass puck times V puck initial minus V puck final is going to be equal to mass goalie velocity goalie final. This is just by so I've made an error. This is going to be negative. And so in order to do this, we're going to want to do this. We're going to swap these. Because we're going to add this to the other side and subtract this to this side. so that we clear out as many negatives as possible. But we're still doing the same thing. It's just a sign error. Okay, so next up we do energy. So this is solving for P. This is for E. And then we have 1/2 M puck V puck initial squared equals 1/2 M puck V puck final squared minus, we have to add these, it's just because this is a scalar quantity, 1/2 mass goalie velocity goalie final squared. And so one thing that we can do is, if we want to find the final velocity of the I'll show you how this is done. So this is a little bit more difficult of a problem because we're going to be dividing two equations by each other, and that's how we're going to get our results here for this equation. So one thing that we can do right off the bat is we can cancel out all the 2's, make this a little simpler, or the 1/2s, I should say. And from here, we'll start rearranging a little bit. So we're going to get the pucks all on one side. Okay, so in order to do that, yeah, we're going to get all the pucks on one side. So we're going to have some negatives here. Yeah, so this is going to be MP VIP initial minus MP VIP final is equal to MG VGF squared. And so we can factor out a mass of a puck here, and we'll have V PI squared minus VPF squared equals M goalie V goalie final squared. Okay. So now what we can do is, if we divide these two expressions by each other, or if we divide this expression by this expression, we're going to end up with something that looks like this. So then we're going to have MGVGF squared is equal to MP VPI minus VPF squared all over MP VPF minus VPI. And so this does a couple things that we can, and this side also gets divided by MG VGF. I'm going to rewrite this over here once we do the calculation, or I'll just rewrite it. So we've done all we needed with our energy and momentum expressions there to get this result. So this is mg over mg, vfg over vfg, or vgf, and this one squared is equal to mp over mp, 1/2 p I squared minus vpf squared all over vpf minus vpi. Okay, so as you probably can see, this is 1, this is 1. This cancels with the square, and so we're left with VGF on this side is equal to VPI squared minus VPF squared all over VPF minus VPI. Okay. And one thing that we can do here, this is a very tricky problem. So VPI squared minus VPF squared is going to be equal to VPI. I'm going to slide this up for a little bit. What we're doing is we're factoring this. So this is going to be the difference of, there's going to be a difference formula here. And so this is going to be equal to VPI. And so minus VPF plus, or times VPI plus VPF. And so as you can see, one thing that we can do here is this should have been a positive. I messed that up. This should be a positive. That should be a positive. Okay, so then when we factor this square here, or the difference of two squares, this factor comes out and cancels with this factor down here. So then VGF is then going to be equal to VPI minus VPF. Cool. And so then we have to plug this into an equation that we had earlier, and then we'll be able to solve for the final velocity of the puck. So this is a very, very roundabout problem. Okay, so the equation that we have to plug it into is M2 VGF. This was M2. I'm trying to remember which one's which. So I labeled this a little different. M2 is the puck. So M puck, VI puck plus VF puck is equal to MG VGF. So then MP, so then this side over here, this side is going to be MG, and then we'll plug our expression in, VPI minus VPF. And so from here, what we can do is we can start to collect some like terms. I've had these reversed. Yes, these are the same terms here. We can collect some like terms, and yeah, we can collect the mass terms instead, or the velocity terms instead. So MP VPI, we're just expanding these, distributing. MP VPF is equal to MG VPI minus MG VPF. So then we're going to collect all of our velocity terms here. So in this case, I think what I want to do is I want to put MP VPI plus MG. No, that's not right. Okay, so yeah, minus MG VPI is going to be equal to the negative MP VPF plus MG VPF. So then we're going to factor out the velocities. So this is going to be VPI, and I'm going to take this negative over to the other side. And so we're going to have MG minus mp on this side, and this is going to equal vpf mp plus mg. And so then we know the initial velocity of the puck, so we can solve for the final here. Vpf is then going to be equal to vpi mg minus mp over mp plus mg. And there's your expression for your velocity. Okay, now that we've done that behemoth of a problem, let's move on to the next part. So the next part of the problem says, suppose the goalie and the ice puck have an elastic collision, and the puck is reflected back in the direction from which it came. What would be the final velocity in meters per second of the goalie be in this case? So we're now solving for the velocity of the goalie. So we know from before. I'm trying to see if this is the same expression. Okay, so if we have mp v pi is equal to mg vgf plus or minus, because it's in the opposite direction, mp v pf. So one thing that we want to do is we want to get the goalie's velocity all alone. And so then we're going to substitute in our result from part A. So then we have mg vgf is going to be equal to mp v pi minus, or no, this should be a plus vpf and so then we know the mass of the puck, we know the initial velocity, we know the mass of the goalie, and so then what we can do is we can say that vgf is equal to mp over mg, then vpi plus vpi times the ratio of mg minus mp all over mp plus mg. And then you just you should be able to plug your numbers in from here. You can end up doing some simplification of this, but I don't think there's a need here for that. I really don't think there is. No, just find this, multiply it by this, add it to this, multiply it by the ratio. Done. This doesn't need any more simplifying than it does. It'll eventually simplify down to something where you only have to plug in 4 numbers, but you don't want to do all that extra work to get something that you could get out of this. Realistically, one way that you could simplify this in a better way would be mp mg vpi times 1 plus mg minus mp all over mp plus mg. And then realistically, so just use this. This is going to be your simplest case without losing time for doing too much work. So then we're going to have mp, mg, vpi, and then you'll have, this will all be over one factor, and this will be mp plus mg plus mg minus mp, all over mp plus mg. So I multiplied, or I took this 1, and 1 is just equal to mp plus mg over mp plus mg. Excuse me. Okay, and so then the MPs cancel out, and these combine into a 2mg, which then this mg cancels with this here, and then you're left with 2mp vpi all over mp plus mg. Okay, so next problem. We'll have a watermelon is blown into 3 pieces by a large firecracker. 2 pieces of equal mass fly away perpendicular to one another, and one in the x direction, one in the y direction. These pieces fly off at the velocity v. The third piece has 3 times the mass of the other 2 pieces. Write an expression for the speed of the larger piece that is in terms of only the variable v. So this one is going to be a tad more difficult, because we have, this is one piece of the watermelon, this is another piece, and then this is another piece. And this is on a flat plane. This is not another axis. This is just the piece of the watermelon. So this has a VF. These two have velocities V, and these are equal to each other. This is Y, this is X. So one thing that you can reason is that we have to write an expression for this, right? So we can assume that the watermelon at the very beginning, before the firecracker goes off, that the pi is going to be equal to 0. And so we know that its momentum has to be equal to 0 relative to the other components. So we know that the x component of this one has to be equal to the x component of this piece, and the y component of the momentum of this piece has to be equal to the y component of the momentum of this piece. So what we can do here is we can say that originally we have py is gonna, this has to equal 0, and px equals 0 as well. And so then this has to be mv plus 3mvf. So, and this is v of y, and then this is equal to mv plus 3mvfx. And so then we know that VFY has to equal mv over 3m, and this should be negative. There should be a negative in here. Same with this, VFX is going to end up being the same thing, negative mv over 3m, because this velocity points in the opposite direction of either one. Then we see very quickly that our m's cancel out, and we get negative v over 3 for both of these. And so then we can put these velocities together. So then vf is equal to v over 3 squared plus v over 3 squared. And so then we have v squared over 9 plus v squared over 9. So then we can take out our v, and then we will just be left with v is equal to 1/9 plus 1/9. And so then this will end up yielding the square root of 2v over 3. And so then you plug in what v is, and that will give you the numerical value of the larger piece. And so then what angle does this have? We can see that both of these components are going to be equal to each other. So then we can just say that this theta here, theta is equal to 45 degrees underneath the negative y-axis. Okay, so we have two balls of clay are thrown at each other and they collide. And they say they stick when they collide. Okay, so we have values for M1 and M2, and they both have velocities. This V has some velocity in the I hat direction, and V2 is in the J hat direction. And so you have to calculate the momentum after they strike each other. So what we can do here is we can find it in its component form originally, and then we can go ahead and use Pythagorean theorem, I believe, to put this back together. Okay, so originally so what's going to end up happening is these two are perpendicular to each other, so the momentums are just going to end up adding, but there is not going to be a component of the other mass. So M2 doesn't have an X component while M1 doesn't have a Y component. So after they stick together, their new momentum is going to be a composite of the two. So in this case, we have that P is going to be equal to M1 V1 I hat plus M2 V2 J hat. And so we have to find the horizontal component of the velocity, Vx in meters per second after the collision. And so this one is just going to end up boiling down to, you're going to have the X component, right? And the X component is not going to be affected by the velocity and the mass of the Y component. So, but then you're going to have to end up dividing it by the total mass of the new system. So then VFX is going to be equal to M1 V1 over M1 plus M2. Right, because our statement for conservation of momentum would be M1 V1 is equal to M1 plus M2 VFX. And so then you would just divide it to the other side, and that comes out very quickly. Okay, so next up we have to do the Y component, and so the Y component is going to be the same process. This is going to be M2 V2 is equal to M1 plus M2 VFY. And so VFY is then going to be equal to M2 over M1 plus M2 V2. Okay, so we have, I believe, a center of mass problem now. Next up is in problem 8. Okay, so in problem 8, you're going to have 3 beads placed on vertices, right, of a equilateral triangle. So like this, where all these angles here are going to be 60 degrees, and all these distances are going to be d. And then we're going to have M1, M2, M3. And so let's see, write a symbolic equation for the horizontal component of the center of mass relative to the left vertex of the triangle. And so we're doing this one here. This is going to be our origin. So one thing that we'll have to do is, so this M2 on the origin is going to give no contribution to the center of mass. So then we say that XCM is going to be equal to M1 D over 1/2, because the X component here is going to be 1/2, or halfway between M2 and M3, because this is going to be an equilateral triangle. So this is going to be halfway in between the two. And then we have the contribution from M2, which is going to be 0. And then the contribution from M3, which is going to be just D. And this is going to be all over M1 plus M2 plus M3. And so then from there, you just have to plug in numbers, write a symbolic equation for the vertical component of the center of mass relative to the base of the triangle. So this is asking for YCM. And so we can see that these two down here are going to give no contribution to the center of mass due to the base of the triangle. So what we can say is that this is going to be equal to just the contribution from the first one. And so this distance here is not going to be D, but we'll have to use a triangle to go ahead and do that. This is going to be 60. This is a right angle. This is our distance Y that we're solving for. This is going to be a distance D. So we have our hypotenuse. We have, but we need our opposite here. So we'll use sine theta is equal to Y over D. Yep. And so then Y is going to equal D sine theta. And so then we'll have that this is going to be equal to M1 D sine theta over M1 plus M2 plus M3. And then you plug in numbers. Okay, so that completes that problem there. You just have to really take your time and think about these things, and it'll come to you. It'll be easy enough for these. You just have to take those sums and think about what contribution does what. So a object speed is increased by a factor of 3. How does the object's momentum change? This is pretty simple. Oh, okay, I see what their point is. So the point of this problem is that they're pointing out how momentum and energy correspond with their velocities. So uh, in momentum is defined by mv. So this is a linear relationship between p and v. And so with m being a slope, so m is going to be the value of whatever slope. And then you could say that this is velocity and momentum. So you can plot momentum as a function of velocity. And so they're saying that since this is a direct relationship, if you increase the object's speed, then the momentum is also going to be increased by a factor of 3. But kinetic energy, on the other hand, if we were to plot that as a function of velocity, you would have a plot that looks like a quadratic instead, because this is going to be v squared, because k is equal to 1/2 mv squared. And so now in this case, v is squared. So whatever you change v by, that change is going to be squared for the change in kinetic energy. So in this case, you would have to take this and square it. So if you're increasing it to 3v, then you have to plug that in there. And so then you'll get 9v squared. And so then your kinetic energy is going to be 9/2 mv squared over 1/2 mv squared. And then so then you'll cancel the halves and the mv's, and you'll get that this is a factor of 9. So this is just pointing out the different types of relationships between velocity and momentum and kinetic energy. And that's also why, say, when you're in a car and they tell you that you slow down, you'll save a life. That's because every 10 miles an hour that you slow down for gives you a significant amount of a decrease in kinetic energy, and therefore you're less likely to die in a car crash. Okay, so last problem. 2 billiard balls of the same mass, m, move towards each other. One ball moves in the positive x direction, and ball 2 moves in the negative x direction with different speeds. The two balls collide elastically, and both balls change direction after the collision. They give you initial speeds for the two balls, and then they ask you what be the final velocity of ball 2. And so first we have to write an expression for the momentum. So before the collision, they have m1. Oh, they have the same mass, so we don't have to clarify m's. So v1i, and then since v2 is moving in the negative x direction, it's going to be moving, we're going to have to put a negative here, mv2i, and then after the collision, we have, they both change directions, so this is going to be a negative mv1 final plus mv2 final. This should be, yeah, they both change direction. Why aren't we getting a negative for that one? Okay, so they're just clarifying that we don't know. This one's going to be negative, though, because we know that it changes direction and moves back in the opposite direction. They're not putting that in the equation. Okay, so we can divide out the masses because they're all equal masses. And then we can start to solve this problem. we can say that if we're solving for V1, we'll have V1F is going to be equal to V1I minus V2I minus V2F. And so then we're going to have to, these two are known, and this will give us some quantity here. But we still have two unknowns, so we're going to have to use conservation of energy as well. So then we can start to add up the conservation of energy. I'm going to get rid of the m's and the 1/2 right off the bat because they all cancel out. So then we're going to have V1I squared plus V2I squared equals V1F squared plus V2F squared. And since they're squared, they're all going to be negative. So then we can solve for V2F. And so what we can do is we can solve here. And so then V2F squared, we're going to get rid of the squared. We're just going to leave it like that, is equal to the square root of V1I squared plus V2I squared minus V1F squared. And so we can plug these two in, and that'll just give you a an actual number. And from there we can substitute this into the final equation of the ball, and that will yield us an actual answer here. Okay, so no, what we're doing is we're going to plug this one into here. So then we're going to have V2F is equal to the square root of V1I squared plus V2I squared. And I'm going to put parentheses around them because we know what this is. And so then we have minus V1 plus V2I. And this is going to be squared. We should do this minus V2F, and this whole thing is going to be squared. And so if we go ahead and start to solve all of this, we're going to end up getting okay, so I've gone ahead and done some work out here because I didn't like the solution that they gave us. So I'm going to take away this square root and square this side again. And so then I've written out what this term squares out to be up here. And so what ends up happening is that we get V1I squared plus 2V1I, V2I, we get a bunch of cross terms if you go ahead and you square this three-term sum. And so one of the key things that comes out of this, though, is that we have a V2F squared. And so if we take away the square root, we have a positive V2F squared somewhere in our sum over here. And so we can subtract it, and then this is equal to 0. And another big thing that comes out of this is that we'll have V1I squared plus V2I squared. And then we have plus a V1I plus V2I, and this is squared again. And then we just have a minus 2VF V1I plus V2I here. And so from here, this eliminates any quadratics that we have to do and yields us an actual answer without using the quadratic formula if you go ahead and you square this out. Okay, because we have everything in terms of VI1, VI2. So I'm going to go ahead and erase this over here, and then we'll write this last answer out. Okay, so we're going to be solving for VF over here, and so we'll move that over to the other side, and then we're going to divide both sides by 2 times this quantity here, which is VI1 plus VI, or VI2, or V2I. Okay. Again, we're dividing by 2 times V1I plus V2I. Okay, so then we have that VF is going to be equal to everything over here, which is V1I squared plus V2I squared quantity plus the quantity V1I plus V2I squared. And then this is where the division comes in, and we get over 2 times the quantity V1I plus V2I. Okay. And this should yield us a positive answer, because assuming that I believe that, yeah, because V1I is greater than V2I down here, so this is going to be positive. These are both squared, so those are going to add up to be a positive. This entire answer is squared, so that's also going to be a positive. So this will yield us a positive momentum, which is what we are looking for here, because this is V2F. And so we know that V2 came in from the negative direction and has to have a positive answer. And so then you plug your numbers in, and this will yield your solution. That is all for this homework today, class. I'll see you guys later today when we do our test review. Study hard, and I'll see you guys in the next one.